Hello there, young students of chemistry. This is a short recording on nuclear chemistry. Nuclear chemistry is not an easy subject. I'm nuclear engineers, and nuclear chemists are people that work really hard to understand what's going on in the nucleus of the atom. However, the stuff that you need to know, according to the state of North Carolina and for your final exam, is relatively straightforward. So we're going to call this quick little nuclear in a nutshell, just a little bit of information about some weird things that happen in the nucleus of the atom. So the first thing that you should know is that nuclear, there are some elements that decay, that undergo nuclear radiation. And this happens if we have a nuclide. A nuclide is what we call the nucleus of a radioactive element. I guess, yeah, the nucleus of any element, but the nuclide is too heavy, and that's what causes it to undergo nuclear decay. So when you have all of these extra neutrons, please remember that we think that the purpose of the neutron is to kind of stabilize that nucleus and keep the protons from flying apart. If we have all these positive particles packed in this teeny tiny space, we need something that's going to anchor them there, and that's what we think the neutron is for. However, if we get a nuclide, a nucleus that is really way heavier than it needs to be, it's going to lose some weight, and that's what we call nuclear decay. So there's three types of nuclear decay here, and this follows right along with your notes, so you should have a note sheet that you can add to this. There is alpha decay, beta decay, and gamma radiation. And you can see from this chart that the symbol for an alpha particle that leaves the nucleus of the atom is a helium nuclide. So helium having 2 protons and 2 neutrons. The symbol for an alpha particle is this little Greek letter, lowercase letter alpha. Kind of looks like a little fish. Okay, that's not going very well. But it is a helium nucleus. So when a nuclide emits an alpha particle, the mass of the nuclide goes down by 4 atomic mass units, and the charge of the nucleus goes down by 2 protons. And that's how the mass number and the atomic number of the element can change, and therefore that nuclide can turn into a different type of nuclide, a different element altogether. So the mass and charge, 4 is the mass, 2 is the charge. And a beta particle is the symbol for a beta particle is that Greek letter B, that's the capital Greek B, and it really is an electron. And we know that an electron has a mass of 0 and a charge of -1. And then the gamma ray, the symbol for a gamma radiation is this kind of, I don't know, it's a Greek letter again. It's like maybe a fish taking a nosedive. But gamma radiation doesn't have any mass or charge. It's really just energy that's emitted from the nuclide. So what's happening here is this thing is losing energy, and this is generally accompanied by a any type of other radioactive decay. So if there's radioactive decay, it typically has gamma decay occurring with it as well, or gamma radiation. Now, you may have heard that nuclear radiation is harmful, and it is. I mean, gamma rays can get into the DNA of your cells and scramble things up and cause mutations. But we can block it. Alpha radiation is the weakest of the radiation, and I mean just a piece of paper, clothing, that blocks it. There are particles all around us and can be blocked very easily. Beta particles, you know, you have a sheet of aluminum foil, put that on your head, and you've blocked the beta particles. Some people wear metal hats. And then gamma particle is really only shielded. It's not blocked at all, but it's shielded by layers of concrete and then lead. I don't know if you have recall going to the dentist or getting an x-ray. Recently, I think of the dentist because you're in the chair and they throw this heavy blanket on you, and then the radiologist kind of runs around the corner and hides because they're zapping you with x-rays, and x-rays can be blocked by lead. So they put this lead blanket on you to keep the x-ray from entering other parts of your body other than the mouth that they're trying to x-ray at the time. Okay, so when a nuclide decays, it undergoes these changes where it turns from one element into another. So what you see here is an equation that shows the way something is going to, an element is going to decay. That is so strange. That an element is going to decay. And this is just a weird little thing that has happened here. I don't know how to fix this. It is upside down. Okay, well, can I rotate that? Let me pause here for a minute. Okay, so what we're showing here is a decay series, and it's really just a little equation that kind of tells you what's happening to that nuclide. So one thing you want to be able to do is fill in the blanks. You guys, this is the law of conservation. Just like matter and mass cannot be created and destroyed, these what appears before the arrow must equal what appears after the arrow. So if we consider this first decay series for uranium-238, this first decay is an alpha decay. It's losing this helium nucleus. So that's going to make the mass, 238, go down by 4. So the new mass of the nuclide is 234. The atomic number is going to go down by 2. So the new atomic number is 90. Now once the atomic number changes, it is no longer uranium. Please remember the number of protons is what determines the identity of the element. So with that losing two protons, or the mass going down by 2, it's now something new. And if you look on your periodic table, you can see that element number 90 is thorium. And that is the first nuclide in the decay series for uranium-238. So the other thing we can see there is that it undergoes several decays, and we can see that the second one is a beta decay. It's losing an electron. So now what we have is this element thorium, which mass is not changing, so 234 is still the mass. And then remember that the sum of this side has to equal this side. So what can we add to -1 to get 90? And that's going to be 91. 91 plus -1 is going to give us 90. So what's really happening here is that the top number and the bottom number are kind of getting closer to each other. And now again, our nuclide has changed its identity, and now we're at protactinium. PA. So one of the things that you should be able to do is fill in these blanks. Now here we have a change where the, so this is just continuing on down at the bottom. Our nuclide went from an atomic number of 91 to 92. So what can we add to 91, or what can we add to 92 to get 91? And that's going to be a -1. We can see the mass 234, that has not changed, so this top number is a 0. So you'd also have to be able to fill in the type of radiation. In this case, it's a beta decay. Again, you're asked to fill in the type of radiation, so we have a mass nuclide of 234 going to 230, so that's a change of 4 mass units. 92, right, going to 90, that's a change of 2 mass units. So this is an alpha particle, an alpha decay. So you are expected to fill in the nuclide that has formed from a particular type of decay, and you're also expected to fill in the type of decay that has occurred with a particular nuclide formation. Okay, transmutation is a big word for the types of reactions that a nucleus can undergo. This is when one atom gets converted into a different atom, and it can either occur by nuclear decay, we just discussed that with the decay series, or by bombarding a particle, a nucleus of an atom, with a neutron or something else that we can mash into the nucleus. That's called particle acceleration. And any element that's greater than element number 93, those transuranium elements, they are man-made elements. That's what we have done. We have smashed something into that nucleus to make a bigger nucleus, pretty unstable, and they are man-made elements. Here's a couple pictures of some particle accelerators in the United States. This one here is a cylindrical accelerator that I believe is in, no, that might not be right. I know that we have one out in Arizona, and this one is a large particle accelerator. They're going to accelerate the particle around those curves to get it going really fast, and they're going to accelerate it with a magnetic field and then mash it into an atom. Two types of transmutation are fission and fusion. Fission, just like a fissure is a crack. Right now, Hawaii is experiencing many fissures that are spewing lava. That is a large nuclide that breaks into smaller nuclides. You might want to sketch this little picture to remind you what fission looks like. Large nuclide. Typically, we bombard it with something, and that causes it to break. And then fusion is just the opposite. Fuse means come together. So we've got two smaller nuclides that are coming together to make a larger nuclide. Right? Fission is what happens in our nuclear reactors. Fusion is what happens in the sun. That's what is fueling the entire energy of the Earth. So here's a little fusion diagram. Okay, the other thing you're expected to do is calculate some easy half-life problems. Half-life is the time that it takes for half of a sample to decay. So if we start with 5 grams, when there's only 2.5 grams left, that is, we have reached the half-life at that time. So here's an example. We have a carbon-14 that's a beta emitter. Its half-life is 5,730 years. So if you start with 10 grams of carbon-14, the time that it takes to decay into carbon-12 is 5,730 years. So if we start with a mass of 2 times 10 to the negative 12, that's a very small amount, grams of this stuff, how many grams of the original isotope remain? So the first thing you need to consider is how long is 3 half-lives. So if you have one half-life of 5,730 years, 3 half-lives is 17,190 years. How many grams is left after the isotope after 3 half-lives have passed, after 17,190 years have passed, how much is left? So we're going to take our 2 times 10 to the negative 12 grams, and we're going to divide that by 2 because that's what a half-life is, 1/2 of that amount, right? But we're going to raise that 2 to the 3rd power, meaning that 3 half-lives have passed. So if we plug that into the calculator, we end up with 2.5 times 10 to the negative 13 grams of this carbon-14 left. One other way you can do that, if you don't like raising that to the power, you can just divide that number by 2 3 times. So if you put in your calculator 2 times 10 to the negative 12, divided by 2, hit equals, divided by 2, hit equals, divided by 2, you're going to get the same answer, 2.5 times 10 to the negative 13 grams left. So another example of a half-life problem, we have a beta emitter in manganese 56 with a half-life of 2.6 hours. What is the mass of a 1 milligram sample at the end of 10.4 hours? So the first thing we have to do is figure out how many half-lives is 10.4 hours. So 10.4 hours divided by 2.6 hours is 4 half-lives. So we're going to take our 1 milligram sample and we're going to divide that in half 4 times. So we're going to divide that by 2 raised to the 4th power. And that's going to give us a 0.0265 milligram sample left from the 1 milligram we started with. It's good when some elements have these really short little half-lives. We use some of these elements as tracers in our blood. I'm thinking specifically of technetium. That is used as a blood tracer, and it is a alpha emitter, and it happens really fast, so it doesn't stay in your body causing problems, but we can take pictures of kind of the pathway that your blood is flowing through your veins and arteries to see if there's a blockage, because it'll be giving off these beta particles, and if it stops, we'll be able to see it, and it'll be able to show us a blood clot through the circulatory system. So these have some really good little applications, as well as, of course, the nuclear reactors that are providing a lot of energy, trying to meet the energy demands of the United States. So that, my friends, is what you need to know about nuclear chemistry. You should finish any practice problems that are in your notes and check those online. And that's all.